Thanks for coming, guys. What I'm going to do is I'm going to talk today a little bit about some stuff that, it's kind of a survey-ish talk. And there's a bunch of material in here, but I don't have to cover all of it. I just want to get you guys excited about it. So ask questions. Otherwise, it gets very boring. You never want to see the speaker fall asleep. That's a terrible thing. So help me out. Okay. So analysis of algorithms. We do algorithms. I do algorithms. And, in the algorithms, we normally do worst case analysis. We say an algorithm runs in time and log n in the worst case. On every single input, it runs in time and log n. That's great. It's a very robust guarantee. Regardless of what input you give, boom, it'll take n log n time. But maybe it works better on some instances. Maybe it works much better on my instances. I'd like to understand how it performs on typical instances, whatever typical means. And your typical might be different from my typical. That's the important thing, right? So how do you analyze these things? How do you make sense of this whole craziness? So in some sense, I always think of what we do is worst case analysis, and we also kind of want to do best case analysis. What's best case? It means that there's some prediction. There's some patterns you have in mind, and your input follows those patterns, predictable patterns. And here I use. So I'm sorry, but somehow red on black doesn't always show up. It's okay. Can you guys see? There's something written out here.
It shows on the screen.
It's it shows on the screen. So when in doubt, look at the screen. Good. So worst case is when robustness, when data is unpredictable. And here I'm using two words, robustness and efficiency, which I actually got from a talk Adam Weirman gave many years ago, and I really like this thing. He says robustness is when you're doing the worst case, whereas efficiency he calls, and what I call best case, maybe efficiency is a better term, when data follows anticipated patterns. If it does, I want my algorithms to do much better. Okay, and basically what I want to do is I want to actually sort of have algorithms that are in these cases and these cases, and in some sense my case, but I don't know how to capture my case in a formal framework. So instead, I'll opt out and cop out and take best case. Okay, and this whole area has come to be known as beyond worst case analysis. Make of it what you will, but okay. And what I'm going to do today is I'm going to give you a couple of ideas of models. How do you model these things? And the couple of ideas of techniques in the context of online algorithms, which is something that I've been focusing on for the past, years. But yeah, good. So that's the philosophy behind what I'm going to talk about. And let me just quickly remind you what online algorithms are. Online algorithms is a sort of situation where requests arrive over time. Each must be served immediately before the next request arrives. So you don't see the future. You have to make decisions without knowing the future. Okay? And the goal is to minimize the cost of decisions taken, let's say, whatever cost means. And different problems have different costs. Oops, this is the wrong direction. The competitive ratio, and this is a concept that goes back to Slater and Tarjan. Danny used to be at CMU with us. He's still there. So the competitive ratio of an algorithm is you look at the cost of your algorithm on some instance, and you look at the best thing you could have done on that instance. Now, this is inherently an apples to oranges comparison. You are making decisions without knowing the future. The optimal cost is making decisions knowing the future, the entire instance, in some sense. Okay, but it's an unfair comparison. It's unfair to you. So any positive results you can give here are actually very strong. Saying, had you known the future, you couldn't still have done much better. Okay, and you want to minimize this comparative ratio. Okay? You want this to be as small as possible. 1 means you're always optimum. You are optimum even without knowing the future. Whereas, notice that this is a very worst case kind of guarantee as I've written it. It's a max over all instances. Okay? Good. So we'll try to relax that to some extent. Okay, and so there'll be two problems that I'll talk about. So there'll be a lot of twos in this thing. Two problems, two models, two ideas. Actually, it's the same idea, but we won't talk about that. Okay. Online set cover. So what's the setting? There's a bunch of sets. Come on. Elements arrive. The first element arrives. You have to pick a set that covers it. Okay. You picked set S1. It covers this element V1. Oops, sorry. I seem to have, okay. So S1 covers V1, right? Now S2 comes, so V2 comes, and now you have to pick an element because you have to pick a set because this element is not covered yet, right? So you maybe picked S2, and already you're feeling bad. You're suffering regret in some sense. You're feeling bad. Oh, I should have picked S2 in step 1 because it would have covered V1 and V2, and I would have paid 1. But now I have to pay 2. V3, you're like, whew, dodge a bullet out there. At least, and then V4 comes, and then you say, I need to pick S3. The optimum in hindsight is S3, 1. It costs 1. You paid 3, so this ratio is at least 3. Okay. Everybody happy with this definition? But I'm going slow because you just want to make sure the definitions are clear. Okay. Good. Online load balancing. So that's problem number 2. There are M machines, these boxes. Jobs come. Every job has size 1, at least in this talk. In general, they could have larger sizes. We won't talk about that today. This job comes. It can go on this, or this machine. It can't go on. It can't be served by these people. Bless you. You have to send this job to a machine without knowing the future. Okay? So maybe you sent it there. What's your goal? Your goal is to minimize the maximum load. The load is the number of jobs that go on a machine. You want to minimize the maximum load of all machines. Okay? Second job comes. It looks pretty similar. And you're like, oh, this job can go on these machines. I don't want to send it there because then the load will be 2. Right? I want to minimize the max load. So maybe you send it there. But then, you got this job. You're like, oh, man. Okay? So you sent it up there. Now this load is 2. But if you actually look at all these 3 jobs in hindsight, there's a perfect matching between jobs and machines. You could have sent every job to its unique machine. So opt is 1. You paid 2. The ratio is 2, at least. Because it's a max over all instances. I just gave you 1 instance. Okay, good. That's it. Good. Okay. So I call this the price of uncertainty. By the way, one thing that okay, so maybe I'll mention it out here. Set cover. In case you haven't seen this before, well, take it on faith, whatever. It's not important. I just want to show you the numbers. Why you get these, catch me later, I'll tell you more about them. In the offline setting, where you know the entire instance up front, there are efficient algorithms that get you within log n of the optimal solution. If there is a solution of cost 100, you'll pay 100 times log n in polynomial time. In the online setting, you kind of lose more. You lose 2 logs. And I'm not telling you why. This is known result. Let's go with that, and then we'll come back to it. Okay. And you can't do better. So then there's this gap between log n and log square n. I'll call this the price of uncertainty, a term I made up for pretty much this talk. For load balancing, the problem that I told you is really a matching problem. You can solve it using matchings or min-cost flows or whatever. So you can solve it exactly if you know the instance. But if you don't know the instance, and I'll show you an example, you can't do better than log of the number of machines. Okay? So again, there's a gap. And so the question is, these are all worst case guarantees. Can you step away from these kind of lower bounds in the worst case by doing some kind of beyond worst case kind of guarantees? So I'm going to essentially give you 2 solutions out here. I'll give you a model in which to study set cover, and then I'll give you a solution, and then I'll give you another model and solution. Yes, please.
All these online runtime, is there some form of implicit explanational barrier beyond just price of uncertainty as to the reason why you gotta go below the bound?
Good. So for this one, I'll actually show you a lower bound. For this one, showing you a lower bound requires maybe I'll I know of short lower bounds, but they do require a board, and it gets a little messy. But really, it's like information theoretic essentially. It's the kind of bad examples I can construct are very much along the lines of those bad examples that I showed you earlier. I can construct instances where essentially actually that I can write on, right? Okay. So let me give you one example. Okay. Let's give this example. This one's kind of nice. Okay, it's a complete binary tree. Okay, good. What are my sets? My sets are edges that go from the root to the leaf. Okay. What are my elements? My elements are edges. This set covers this edge because this edge is on this path. This set does not cover this edge because it's going to the wrong leaf. Okay. So here is an instance I can give you online, which is like a dirt simple instance, but you'll pay log. Okay, dirt simple, you can do it. Offline you can do it one. First I'll give you, so I have edges like this going to every leaf out here. Okay, so in my mind I'll pick a random leaf. I'll give you this edge. Now there are all these leaves out here. Okay, so what I've done is random leaf, and I'm going to give you first this edge, then this edge, then this edge. Now, what's the optimal solution? This. But when you see this edge, you essentially have no idea which of these leaves I've chosen. And you can make this formal that essentially you'll screw up. In fact, when you see this edge, you'll choose one of these leaves to cover, but it will be a bad leaf with high probability. So basically, since you don't know the future, you are forcing yourself to make. The adversary in some sense is forcing you to make mistakes a lot. So here was the gap between 1 and log. Getting this to log square requires a little bit of work. At least it gives you some idea, hopefully. Okay, you had a question, please.
Yeah, wait, sorry. Just in the load balancing problem, what's preventing like the input to just be like a sequence of jobs that all like only can be sent to the same machine?
Good. So suppose it's the case that there's some number of machines, and every job goes to the same machine. What's the optimal load in this case?
Well, I'm thinking it's just number of jobs.
Yeah, so it's a number of jobs. And what will your algorithm do? Also number of jobs.
Yeah. Oh.
So it's a ratio, remember?
Oh, it's the ratio.
Yeah. So you want instances where the optimal solution is very low,
right,
but your algorithm kind of screws up every time.
Okay, I see. Okay. So that's those numbers in the ratio.
Yeah. Okay. So in fact, let me show you. Since I have a board out here, this is crazy. I can give you guys all kinds of examples. So this example will come later, but let me just give you an instance. Okay. So here's what I'm going to do. I'm going to give you a job that can go on the first 2 machines, a job which goes on the next 2 machines, a job which goes to the next. There's like 8 jobs out here. 8 machines, 4 jobs. What are you going to do? I even gave you 4. These 4 jobs arrive all at once. I'm giving you more information. Where are you going to send this job? Up. You chose poorly. So let's say that all the jobs went up. Okay. Here's what I'm going to do next. I'm going to give you jobs which only go to the up machines. I'll say, my friend, you should have gone down. Right? What are you going to do now?
Still like
You don't learn. So now you have 2, and now, oh, sorry, no. So it's every other one, right? Yeah, good. So now I'll give you a job which can only go on these guys. So basically, you got log n load, right? Because every time I half the number of machines, and I increase the load by 1. Whereas in hindsight, if you had gone down for every one, you would have got a load of 1. Log n versus 1, this is this gap.
Seems like it breaks down a little bit if you allow, if you choose randomly.
If you choose randomly.
The adversary to construct.
Excellent. So it breaks down if you choose randomly, but I can also, okay, let me give you another example. Since we are doing this thing. There's a bunch of machines, again. The first job comes and can go to every machine. Okay? Where are you going to send it? Yeah, good. So you're going to send it randomly. Let's imagine this as kind of sending it fractionally. Let's look at the probability of sending the load a job to a machine as kind of a fraction. So you'll send 1 over m of this job to each machine. Okay. Maybe you didn't. For a lower bound, what I'll do is I'll take a random one of these machines, and I'll say, that machine was secretly the machine you should have sent job 1 to. I'm never going to give another job that can go on that machine. The next job can go on all but that machine. So every time, the first job loaded every machine to 1 over m. The second job will load every machine to 1 over m minus 1 or so. This is how much you'll pay. I'll have paid 1. So it's the same kind of thing. So, very information theoretic arguments that are going on out here. Good. Okay. Other questions? As I said, there's a lot of material. We won't get through it anyways, so you might as well ask questions. We good? We good. Okay. So I'm going to fill in these blanks. And by the way, if you're interested in this kind of thing, you got to choose a model to do this, and there isn't a canonical model. So what do? You pick up this book, which Tim Roughgarden, who's now at Columbia, or has been at Columbia for quite some time now, he put together, a bunch of us wrote chapters for this, and there are like 30 chapters, so there are 30 different models for studying beyond worst case. And there's many, many different ways. I'm not going to sort of even try to sort of go over all these things. But basically what I'm going to do is I'm going to focus on 2 things. Actually, let me not even worry about that. So let me just tell you what I'm going to do. I'm going to show you a model called the random order model. And in that model, I'm going to show you that you'll get a log n approximation for set cover. And this is old stuff. This is with sort of work done with my students when I was still back at CMU. There's some new work on this. We'll see whether we have time to talk about that. And then for load balancing, I'm going to show you an algorithm that will get within 1 plus epsilon of the optimum. I'll have to make some assumptions. As you see, there's some certain terms and conditions apply, and we'll see what those conditions are. And this model is called online with a sample. And it's a model that I like a lot, so I want to sort of, part of this is an advertisement. I'm telling you, work on this model. I think it's a cool model. There are interesting questions out here. Okay, good. Yes, please.
Is that interesting model related to some practical?
Good. So it will be related to a practical thing, and I'll try to motivate the model when we come to it. Good. Good. So what's the random order model? So let me first actually pin down the problem setting for online set cover. Let me just be a little more formal. So here's the information model. Initially, I tell you, there are 6 sets in this set system. You don't know anything. which elements belong to which sets? No idea. The first element comes and it tells you which sets it belongs to. Okay? You have to choose a set that covers it. Maybe you chose that guy. The second element comes, maybe you chose that guy. Third element comes, you lucked out. You actually had already covered it. The fourth covered, the fifth you didn't, in this case you have to pick this set, and then the sixth you lucked out again. Okay? That happens to be my instance. Okay? This is standard online set cover. The model, okay, so as I said, there's, one piece of notation, by the way, I should have mentioned. There are n elements out here and m sets. For the purposes of this talk, m and n are the same. No, just ignore the difference. Don't worry about it. Or polynomially related if you really are particular about these things. Okay. So what's known? So back in 2003, this group of people, they gave an algorithm which was log n log m competitive. Had a comparative ratio of log n times log m. In my mind, that's 2 logs, n and m, whatever. Okay. And then they showed a lower bound of log n log m for deterministic algorithms, and also for all polynomial time, even randomized algorithms. Now you'll notice that this doesn't cover all algorithms. So there could be an exponential time randomized algorithm that gives a single log. I don't know of a lower bound ruling that out. It's a great question. I thought a little bit about it. I don't know how to solve it. So if you guys have any ideas, that'd be awesome. Okay, good. But that's not the question today. The question is what happens beyond the worst case. And what's the model? So the model is the following. It's called the random order model. And it's, okay. The adversary first fixes an instance. It's the same instance as before. The adversary fixes it up front. But it doesn't tell you the instance, of course, otherwise there's nothing to solve. What then nature does is it tosses some random coins, and it presents you the instance in random order. So the adversary first fixes the instance. So earlier, remember, the adversary fixed the instance and then gave you the first one, the second one, the third one, and so on and so forth. The difference is the adversary now fixes the instance, but the nature randomizes this. And you should think of this as these are people who have to come to your shop and ask for service in a certain way. But trains are late, people get distracted, they go to coffee shops, things like this, they come in random order. Now you can say, why uniformly random order? It's a modeling decision. We can talk about other high entropy distributions and things like this. Things get more complicated. So for simplicity, for mathematical simplicity, uniformly random order. Nature fixes an instance, but the elements arrive in random order, uniformly random. And the question is, what happens? Can you get power from this randomization? That's the real question. Okay, good. So now V1 might come first, but then V4, then V5, then all kinds of crazy things could happen. Okay? Every order is equally likely. The model clear? Okay.
Sorry, so what is the optimal solution we are looking at here?
So again, the optimal solution is the solution to this instance. Remember, the adversary fixed an instance. The optimal solution is fixed.
Yes, and what is the expected value that we are carrying here? Is this taken over?
All possible random permutations. Absolutely. Another way of viewing this is just a algorithm design technique. I'm going to give you an algorithm that will work for random order instances. If you have an offline instance, run this algorithm in random order and you'll also get a solution. But yeah, good. Good. Okay. So here's the, I'm going to tell you an algorithm. I'm going to make 3 assumptions. The first assumption is all costs, I should have said sets could have non-unit costs. I didn't say it, I ignore it. Sets have cost 1. Each set costs me 1. The second thing is I'm going to take exponential time. It's okay because I'm fighting uncertainty. Here in this instance or this instance, you could take all the time you want, guys. It's not going to help you. It's all information theoretic, the lower bounds. Right? Good. We can make it polytime, and I'll show you the algorithm, the polytime algorithm, but that's neither here nor there right now. The third thing I'm going to do is I'm going to tell you, this is a trick that Manuel Blum used to tell me. I could tell you something. That's the hint. Okay. Suppose I knew the value of the optimal solution, not the actual optimal solution, that it contains 7 sets, let's say. How much power does that give me? I'm going to assume that I know the value of opt. Okay. And the value of opt is opt. Okay. 7. We'll get rid of all these assumptions, not important, but for algorithm design, let's start off with these 3 assumptions. I know that the optimal solution contains 7 sets, which means there are m choose 7 possible solutions that are out there. I don't know which one. Okay? That's the real problem. It's uncertainty. There are so many options. I don't know which one. So just in this box out here, I have put down all possible solutions containing opt sets. There are m choose opt of them. One of them is the optimal solution. My goal is to find that needle in this haystack. Good. In this box, I'm going to put down all the elements I need to cover. I don't know them. They have not come in yet. And in this box, I'm going to put down my solution. I'm going to slowly build up my solution. Initially, I have nothing in my solution. Also, I have nothing in my algorithm, so I better start telling you the algorithm. So the algorithm says, okay, what's going to happen at each point in time? A random new element from this set will arrive, right? Everything's fixed, remember. This bipartite graph, it's fixed. A random new element will arrive. This element arrived. If it's not covered by my solution is nothing, so nothing's covered. Do the following. Firstly, from this collection, this element has told you which sets it belongs to, right? So there are some collections out here which don't cover my solution. Throw them away. Yeah. So let's throw all these guys away. This is garbage. From the remainder, my solution could be any one of these solutions. The optimal solution, pick a random one of those. Okay? There are opt many sets out here. Let's say 5 sets out here, right? Let's say opt is 5, not 7. Pick a random set in. Okay, so firstly, one of these sets must cover this green guy, because that's why I didn't throw it out, right? So pick that guy. S5, let's say. It covered this green guy. Yeah. Now the green guy is covered. Whew. We're happy. But do one more thing. Pick a random set from this collection and also add it to your solution. Just a little more. I had to pick one set, I might as well pick 2. Okay? This one set that I picked might not, is just covering this element really. I want to kind of learn from my solutions. So you'll see why I picked a random set from that collection. So I picked a random set and I also added it. Else.
Are you in the uniform cost case?
Yes. Unit costs. Everything's unit.
Oh, yeah.
Good.
Should have read the slide.
Too much effort. You paid 2 out here, okay? So every step you're going to pay 2. Every step an element arrives that's not covered, you pay 2. Okay? Let's run the algorithm a little more. Next step. A random element arrives from U. Maybe this guy. Oh, we got lucky. It was covered. Nothing. Do nothing out there. Next element. A random element arrives from this set. Unlucky. I need to do work. What do? Firstly, I throw away all. Oh, sorry. I'm going the wrong way. Firstly, I throw away all garbage sets. All garbage collections that don't cover my hand. From the remainder, pick a random guy. Pick the set that covers this guy. Pick another random set. Okay? Good. So every time an element comes which is not already covered, you're going to pay 2. So your whole goal is to figure out how many elements were uncovered when they arrived, because then you're going to pay 2. Good. Good. So we'll analyze this. Yeah, please.
What's the intuition here from picking another random set?
Very good question. Let's ask that question. Okay. How many elements? Okay. So you'll see the analysis. Okay. Let me give you a little more intuition before that. Here's something I'd love to do. I'd love to say that every time I had to pay something, I reduce the number of sets out here by half. Suppose I could do this. How many times can I halve this number? Log of m choose opt is kind of like log of m to the opt, which is opt log m. Opt log m is very good. I'm very happy with opt log m. So if every time I paid, I halved this set, I'd be very happy. The problem is I won't be able to do that. So what I'm going to show is either I halve this piece up here, this region, the remaining region, or I halve this uncovered region out here. Not half, but I reduce this by some amount. And you'll see why that will come up in. Just hang on for 1 minute more. And oh, by the way, this was work with Greg Keeney and Roy Levin. And this is a few years back now, but I love this algorithm. This is a beautiful algorithm. Even though it's my algorithm, I'm tooting my own horn. But some days you're like, yeah, this is the right algorithm. Okay.
Roy Levin also went to Brown.
Roy Levin also went to Brown. Yes. Bless you. Yeah. He was an undergrad here, as was Ellis, I guess. Same year.
TA. He was my TA.
Oh, so a year ahead of you or something? No, whatever.
It was just slow.
Just we tend to be. It's okay. Good. Okay, let's get back to business. Yes, please.
We get to the inversion of those sets. Are you assuming that you have some sort of nice description of those sets? You can do time?
Good. So right now I'm assuming exponential time.
Oh, okay.
Yes. Good. We'll come to Pauline time in a moment. Good. Other questions? Yes, please.
Does it end up mattering if, when you choose a random set, you can also allow it to be the same set that you already chose, or they must be two distinct?
It doesn't matter. If accidentally, the random set that you chose also covers this element, you could get rid of this thing. It'll save you a factor of 2, but I'm not worrying too much about it. Be good? Okay, so let's do the analysis. So we're going to ask the question, and it took us some time to ask this question, but once this question was asked, the answer was. Okay. So I have some number of solutions remaining, right? And I have some number of elements which are not covered by my current solution. And the important question that we had to ask was, do half of these remaining solutions cover half of these guys. Okay? How many answers can this question have? Two. Okay? Suppose yes. Suppose a lot of collections out here cover half of these elements out here. So when I pick a random set collection from here, with probability 1/2, it will cover half of this part. So when I pick a random set from that random collection, it will cover half times 1/opt of this part. This part will shrink a lot. You will make progress. We call this the cover step, this blue part out there. Learn or cover. Okay. The other answer is no. Now if half of these collections are crappy, they cover very few elements from down here. So when you pick a random element from here, chances are it's not covered by half of the remaining solutions. So you're going to throw them all away. You're going to make a lot of progress up here. We call this the learning step. So either you make a lot of progress down here or you make a lot of progress up there. It's kind of like a win-win analysis. Yeah?
This U is all the elements in question, right? Like
Exactly.
U is everything you need to cover eventually.
Eventually. Okay? So let's just do that one more time. Do half of the remaining solutions cover half of the remaining elements? Well, yes. Suppose the answer is yes. Then a random solution covers half times half. With probability 1/2, it will cover 1/2, 1/4 of the remaining elements. Then a random set in that will cover 1/4 times 1/opt. It's a random set in that. So the uncovered elements shrink by that. And now if you just do the math, all you need to know is, I teach this in my classes. I tell you this is the most important inequality in the whole world. 1 plus x is less than e to the x for all x. Even negative x. Okay? So if you see 1 minus x, you should just use that. So whatever. Good. Okay? There's some math, not important. Very easy math, but not important. Okay? And if the answer is no, most of the collections up there are crappy. So then a random element discards 1/4 of the remaining solutions. So the number of not uncovered solutions, the number of thrown away solutions reduces by 3/4. So you'll shrink down the solutions space out there. Good. And that's the whole analysis. And in some sense, it's okay. I won't philosophize too much. I think I'm going really slow. So it's maybe we'll stop at halftime. I've got 2 things to talk about, but I don't have to talk about both. I'll just talk about one. I wanted to talk about this. Let me tell you the algorithm. Yeah? Let me tell you the poly-time algorithm. I won't analyze it because it requires a little more math. You guys, you've suffered through a lot already. It's okay. You haven't suffered through much. This is the stuff why we come to grad school, right? And like, give me more of this stuff. Okay, so here's what I'm going to do. Instead of maintaining this collection, this massive collection, this m-choose opt size collection, what I'm going to do is I'm going to maintain a distribution over sets. It's the probability distribution over sets. And when an uncovered element arrives, firstly pick any set that covers this element. Doesn't matter. I'm still in the unit cost case, by the way, else. But pick a random set according to this distribution. Okay. And I'm not going to, I was presenting all this from the perspective of something called online convex optimization. If you've seen this before, it's useful, but if you haven't seen this before, just ignore it. Here's what I'm going to do. where is this distribution coming from? And here's what I'm going to do. I'm going to say, you had some distribution earlier. Let's say that this distribution, this is a distribution over sets, right? So let's say this distribution was placing 0.1, 0.3, 0.7. Okay, I've already run out of probability mass, 0.2. This is my distribution over sets. This element came in. Somehow this suggests that sets containing this element are important. Sets containing other elements, sets not containing this element might not be as important. Yeah? So here's what I'm going to do. I'm going to look at the sets that contain this element. Let's say these two sets. And I'm going to increase their weight by a factor of 2. So I'm going to make this 0.6, 0.8. Okay? This I want to say is my new distribution. Now, of course, this is not a distribution, so just scale it down so that it becomes a distribution. Okay? This is often called the multiplicative weights paradigm. And if you haven't seen this before, you will see this in a class soon. If you have seen this before, turn to the person next to you and explain to them what's happening. But it's okay. So really, that's what you're going to do. You're going to start off with the uniform distribution over all sets. Whenever an element arrives, you'll pick any set that covers that element. You'll pick a set from the current distribution, and then you'll do this update. You'll take all the sets that contain the current element and double their weight. This is this is called multiplicative weights. I have lecture notes on this in case you're interested, or there's like a million lecture notes out there. You don't have to look at mine, but it's a very powerful idea. And, if you use this idea, that gives you an efficient algorithm instead of this exponential time algorithm that we want. And in some sense, the intuition that I have is that explicit representation I was keeping was this very wasteful kind of representation. I really was trying to understand which elements. I was trying to maintain counts of how many times a set was seen. It's not quite that, but that's my intuition. So sets which have covered a lot of elements in the past somehow should be more important. And that's what this guy is doing explicitly. Yeah.
Is it fair to say that the way that you represented the set covering problem and the load balancing problem seem almost identical? You're just trying the incentives are pretty exact, or pretty opposite each other. Where in the set covering you're trying to create the most concentrated, you're almost trying to maximize
exactly.
the balance of the
exactly. In set cover, you want a small collection of guys on the other side who capture everybody. Whereas in load balancing, you're trying to spread it out.
Given that, is there some carryover between results in one area to results in
Good.
the other area?
It's an excellent question. At some level, I don't know of one. On the other hand, I just told you about the multiplicative weights approach. That will also apply out there, but for different reasons. Yeah. Else?
So did we not know a polynomial time implementation of a learner covers anything until
No. So what even our original paper gave a polytime representation of this. What this paper does. So this year, what we did in this paper was essentially give a very sort of so the previous analyses were grungy. We had to do a lot of algebra and stuff like that to make it work. What this paper does is it smoothens it out, and it just gives 3-line analyses of these things. So if you're interested, I'll flash this, but none of this is important. You can use something called online convex optimization to get the same results out here. There's some stuff happening. Just ignore it. Not important. Maybe here is one thing I wanted to say. Ignore all this text. Just look at this picture. Okay. There is a beautiful solution from which you should be sampling. What's the solution? The solution that, here are all the sets. Here is the vector consisting of, indexed by all the sets, 1, 2, up to m. Here is a beautiful solution from which you should be sampling. It places 1 over opt on the sets in opt. If you were sampling from this distribution, you would sample essentially opt log opt sets, coupon collector. Okay? You don't know this distribution. You have to learn it, right? Okay. How do you learn it? You learn it because you get signals. And what are signals? Signals are elements arriving saying, dude, I want to be covered, you haven't covered me yet. It's kind of like a stochastic feedback. It's like, I'm saying words which may or may not mean things to you. It's like a gradient information, but it's like a stochastic gradient information. That's what we're trying to capture out here. So in some sense, what we are doing here is online algorithms, but it's also learning. And we are trying to use learning ideas, and if you're doing learning ideas, it's very natural that you should use multiplicative weights. Okay? If that didn't mean much to you, come and chat with me, I'll tell you more. Okay? But really, there is a learning thing. This is what you wanted. You need feedback to learn this. Because if somebody doesn't teach you, how are you going to learn? What's going to teach you? Well, nature is going to teach you because it's giving you random sets from the remainder. It's like samples. That's the idea. Yeah, good. Maybe you guys end on the hour, right? Pretty much.
Ish. I think we have the room till 1:30.
No.
Yeah.
Suffering will be involved.
Yeah.
We don't want to do that. Yeah, good. So, here's what I'm going to do. In the rest, I'm going to just give you a sense of the model that I wanted to study and the result. And we won't talk about the techniques. Okay. So remember the problem? There's this load balancing, jobs arrive, they need to go to machines, you want to minimize the maximum load. Okay. We showed a log, and there's a typo out here. This is log m number of machines. Actually, we did not show this. Greedy is log m competitive. Some fact. I could prove this, but not today. Okay. Oh, by the way, maybe I'll give you some idea. How many of you guys have seen matchings before? Some of you have seen matchings before. Do you remember the relationship between a maximal matching and a maximum matching? How large is a maximal matching? Just pick an edge. So what's a matching? A matching is you have a bunch of points out here. There's some crazy graph between them. You want to pick a collection of edges so that no two of these edges hit each other, right? So here is a graph where you could pick this, a matching of size 2, but if you greedily just picked this guy, you can't pick anybody else. This is a maximal matching. You can't add anything more to it. This is a maximum matching. This is the largest size matching. This shows that there is a maximal matching of size half the maximum matching, maybe, and this is the worst, So you can show that greedily picking edges, you'll get maximal is half maximum. If you know this fact, you can think about this as an exercise. How would you do this? Okay. Now I won't say more than that. And there's a lower bound, and the lower bound is log m again, and you already saw the lower bound. In fact, you saw 2 lower bounds. So we're good on that. It's the same thing going on out here. Okay. So here's the model. ignore all this junk. This is the model called online with a sample. The adversary fixes the input. You get to see a p fraction of the input. So the adversary has written down the entire input. You get to see each one of these input requests with probability p. This is your market research, if you will. Somebody has done the market research. They've sampled a p fraction of people, and they know exactly what they're going to request. Given this sample, can you do better on the actual instance? So this is a model called online with a sample. It goes back to this 2019 paper of Chaim Kaplan and others. And really, in the online setting, you can think of this as just, online just says, I don't know anything about tomorrow. Online with a sample says, oh no, you've done your research. You know a small sample. You've seen 1% of the input, a random 1%. What does that teach you about the actual instance? Okay. So that's the model that we study in this paper. It's not a distributional assumption. It's really just sampling access to a finite data set in some sense. And here's what we can show. Okay. We can show that if the optimum load is large, then I can get 1 plus epsilon times the optimum load. And technically, it's saying I can get load 1 plus epsilon opt plus this garbage term. And this garbage term is kind of, you should think of this as, if the optimum load is 1, then sampling tells me very little. But if you have the optimum load is a little high, then sampling will start to give you some information. And this is what I need for sampling to actually start giving you information. And I'm being vague out here, but let's go with that. And so maybe the main idea, and I have 2 minutes left, which is just enough to flash this slide. Firstly, I want to say if optimum load is high, then an integer assignment is the same as a fractional assignment. If you don't believe this, it's really what is known as the Chernoff bound, but don't worry about it. Just imagine every job can be sent fractionally to machines. So here is the algorithm. This is what it's going to look like. It says that there are 2 parts to this. The first theorem says, I can give you, magically, I could give you these things called weights on every machine, such that when a job comes in, it looks at the weights of the machines that it goes to, or it can go to. And the weights are 4, 2, 1. Think of these weights as importance. It'll send itself proportional to the weights. 4 7s there. 4 plus 2 plus 1 is 7. 4 7s, 2 7, 1 7. Proportional. There exists machine weights, so that proportional assignment is very good. Okay. But I don't know these machine weights. That's the real problem. But now, as I said, there's something to learn. What do you want to learn? You want to learn these machine weights. What do you have? You have a sample. Okay, ignore. There exists an algorithm used to find the machine weights using the sample. Those of you who have taken a machine learning course or know that this is the problem of generalization. I give you a sample, I want to learn something so that it works well on the actual test data. The test data is the 1 minus p fraction of the instance. That will come tomorrow. Okay? And what we do is we actually show these 3 things. The first one is is fairly simple using standard results. These 2 are interesting things, but have a look. So I'll put the slides on my webpage. Have a look if you're interested. There's some cool stuff going on, stuff that I like. But yeah.
If
the integer assignment is approximately the fractional assignment,
Uh-huh.
it leads me to believe that like, are there any like LP-based solutions?
Excellent. So you could ask for an LP-based solution, and you could say, look, here's the thing. I want to learn something. I want a structure that I can learn. An LP-based solution, a priori, is not quite what I could learn. Or at least, I didn't see how to learn an LP-based solution. So here's something I can show you. I can just flash ahead to say, how do I prove that there exist these machine weights? Okay. Maybe I'll tell you this. I'll show you this slide. I said, I promised the previous slide was the last slide, but since you asked a question, now I get to do one more. Okay. Why do there exist these beautiful weights? So that proportional assignment is good. Okay. So here's what I'm going to do. I'm going to write an LP. I'm going to write fractionally. I'll assign every job to a machine. So job j goes to machine I to an extent of xij. Every job should go to at least one machine. Its fraction should sum up to 1. That's this. Every machine should get at most opt load. That's this. The assignments can't be negative. That's this. Okay. This is an LP. What do I do with this LP? What I didn't know was what to do with the LP. But then I can use this idea, and actually this is due to this very nice paper from Shipra Agarwal and others. I'm going to try to find, and there's a method to this madness. I'll say, of all the solutions that look like this, I'm going to find the one that minimizes this function. You might say, what madness is this? This function is the negative entropy function. So I'm minimizing the negative entropy, which is like maximizing the entropy. This is the old idea that a lot of disciplines have used. Find the max entropy solution for 2 reasons. There's a lot of structure in there, but B, you don't know the future. So you might as well maximize your entropy subject to the constraints. Okay. If you find this solution and you do some algebra, you're like, what's the solution to this thing? Then you pick up the convex analysis book. You figure out what's the optimality conditions, you take the derivative, blah, blah, blah. You say, at optimality, the xij is equal to e to the dual variable. So really, you should think of these weights as coming out of dual variables to a convex program instead of a linear program. So almost, you're heading in the right direction, but you just have to take a slight left. Anyways, that's the sort of main thing, and then there's something else going on in the rest of the talk, but don't worry about that. So the thing that I've been talking about recently is this idea that worst case analysis is beautiful. I love worst case analysis, but sometimes you should be cognizant of extra data that you have. You might have a sample. You might have structure on the input. You might have randomness in the input. Let's use all of that. Okay? When do our algorithms? I love proving lower bounds, by the way, but I don't love it as much as I like showing algorithms. So if I can show that in my model we can't solve this problem, then I say what's a reasonable assumption to make so that I can solve this problem, because I really want to solve the problem. That's my whole thing. Okay. Anyways. So then there are various kinds of questions come in. Okay, so today I was basically talking about inputs being stochastic, but then you can ask the question, this algorithm that you gave, is it really overfitting to the model? What happens if I tweak the model a little bit? The adversary can come and change a few things. What else can we learn? Various kinds of things. So nowadays there's a lot of interest in, can I learn? Maybe machine learning can, maybe ChatGPT or whatever, Gemini, can learn something that you can't learn. Sure. But it can also learn garbage, which often it does. Yesterday it was telling me my proof was wrong, and I was like, dude, my proof is totally correct. And for sometimes it's correct and sometimes it's wrong, and we need to figure it out. Okay, So basically, I might get predictions, and those predictions might be garbage or they might be good. So now I need to figure out. So like for instance, if I gave you a sample, just let's go back to the previous model. I gave you a P sample, but this P sample is the corrupted P sample. Your market research was not perfect. Can you do the same kinds of things I can do? I don't know. It's a tricky question. I don't know how to solve this one. But in any case, these are the kind of questions. There's lots of beautiful questions in this area. So if you're interested, have a look, and we can talk more. Okay, let me stop here. Thanks, guys.
Okay. I guess we're 5 minutes over, so if anybody has to go, you should go.
I think people had to, yeah. I'm always over, you know. But Ellis knows, you know, he's been in my classes. We always go over lectures. But, cool. Okay. Anyways, if you're interested, have a look. I'm happy to answer questions, and we can see how it goes.
I'll ask a question.
Please.
For the people that are staying. I guess, okay, I have a very malformed question, which is like, have people looked at instance optimal in the online setting? Like, for all of these sorts of like, I mean, I'm not sure exactly what this would mean, but like, I want something like, well, if you give me an instance, or really a collection of instances that the adversary gets to sort of choose a worst case among, there's some kind of like worst case online performance that's just purely existential, like these ones. And now I just always, given sort of what the adversary is choosing among, I want to be competitive with respect to, like, you know, the best algorithm that's supposed to work for all of these. Is there any hope?
So one thing is you'll have to restrict the class of algorithms, because if you just say what's the best algorithm amongst any algorithms that can solve this instance, well, there's the algorithm that does exactly the optimal thing.
Yeah. Well, I guess what I'm saying is, like, if you imagine what you want is there's like a collection of possible instances, and the adversary gets to adversarially choose among them.
Good.
Now your algorithm is supposed to work across all of those instances.
Perfect.
For that class of algorithms, there's some sort of, you know, there's some
Good.
worst case performance.
Good.
You want an algorithm that performs best.
So there is some work. It's, you know, it's kind of not really articulated the way you're saying this, but it's similar to this. Like for instance, here is one possible restriction, you know, or one possible kind of thing which is somewhat instance optimal. Suppose I want your algorithm to be good compared to all algorithms that on this prefix will make the same decisions as, you know. So you can't say, oh, tomorrow I know that this thing will come, so I'll take weirdo decisions right now on this prefix. So on every prefix, you have to be consistent. I don't know of good results on this thing. So there are ways of restricting it, but just the analysis gets, It would be good to actually get some nice results out there. Very often, you know, it's easy to come up with models, but then people are not convinced by the model until they see a good result in that model. So then comes this problem: how do you find a model and a good result in that model? And then, you know. So in some sense, I don't know if you guys have seen this secretary problem. Okay, what's the secretary problem? And numbers will come. It's max finding. I want to find the maximum number. The first number comes, it's 52. Should I pick it or should I not pick it? Tomorrow it might be 693. Right? So how do I make a good choice of the max number? I want a bunch of numbers will come in, A1, A2, up to AN. I want to pick the max amongst them. The numbers could be arbitrarily large. You can think of this as paintings come into my shop. There's a Rembrandt that may or may not come in. If there's a Rembrandt, I want to pick it. I get to pick only one person, by the way. Otherwise, I'd pick everybody. So in the worst case, there's no chance. But on random order instances, you actually have you can pick the Rembrandt with probability at least a quarter. Okay? So here's what you do. You wait until half time. Suppose there are n elements arriving, right? So wait until n over 2. look at the maximum value you've seen. So you don't pick anything out here. Look at the maximum value you've seen so far. In the second half, pick anybody who's above the maximum value in the first half. When will you pick the Rembrandt? If it comes in the second half, and the second highest thing came in the first half. Then you will pick the Rembrandt, but you will not pick anybody else. Half, half, that's a quarter. Okay? This was called the random order model, and it really made the random order model, after this, anytime you want to convince anybody of the random order model, you say, the secretary problem. Everybody says, yeah, okay, game over. So you need a good model and a good problem. I don't know of a good problem in the kind of questions you're asking in some sense. But anyways, yes?
Is there any work on, instead of having a given instance being in a random order, like having some distribution over instances?
Yes, so there is work on distributional set cover, distribution load balancing, all kinds of things. Often those results tend to be, in some cases easier, or in some cases incomparable with the kind of results out here. But there is work, and it's a very reasonable assumption to make. Maybe IID, maybe you give a different distribution for every time. Good questions out there as well. What if I give you a distribution and the distribution is going to shift? These are called sort of slowly shifting distributions. Distribution shift, I guess, is the technical term that machine learning guys use. Not well understood in the online model.
I'm trying to think about like a multiplicative weights model for the thing.
Mm-hmm.
Do kind of the opposite of the set cover. It's
Uh-huh.
like if you get a job,
Uh-huh.
or if you get a job and it like sends the some amount of machines,
Uh-huh.
then that tells you maybe that those machines are going to like, you can anticipate like a decent amount of load for those machines, so you should like increase the weights of all the machines that the job didn't send to. Is that a thing that
I think that's very reasonable algorithm, and in fact, you remember that sort of those proportional weights that I showed you. That's how you learn those weights.
Okay.
That's